First, I'd like to thank you for organizing this online meeting, which allows people for all over the world to participate. And I also like to him for thank Matthias for all his support. I'm really happy to be here, to be part of the CityEngine family, and excited to share my presentation. Which presentation which is focused on the digital twin model. And I have pre-recorded the video of my presentation, and now I'd like to kindly ask Matthias to play it for you. I hope you enjoy it.
In the name of God, the compassionate and the merciful. My name is Farshad Shariatpur, and I'm currently a PhD researcher in urbanism at the University of Art, Tehran. At this stage of my doctoral studies, my research focuses on procedural modeling and artificial intelligence in urban planning and design. My interest in CityEngine began in 2016, as I was seeking smart and automated tools for urbanism. Then I joined the Smart City Lab at Iran University of Science and Technology, and there my studies on CityEngine deepened. It quickly became an essential tool in my research, and I truly fell in love with CityEngine. Today, I'm going to talk about strategies for creating digital twins of urban environments using CityEngine, particularly in situations where data is scarce. We will explore how this technology can help us overcome challenges in developing countries or areas with limited data resources. Let's dive into the practical solutions that can make this process efficient and effective. This presentation is based on the research paper shown here, titled Urban 3D Modeling as a Precursor of City Information Modeling and Digital Twin for a Smart City Era, a case study of the Narmak neighborhood of Tehran City, Iran. The paper explores the application of CityEngine software for developing 3D urban models in data-scarce environments, focusing on the Narmak neighborhood. In this presentation, I will summarize the key findings and methodologies outlined in the paper. Cities are highly dynamic systems, constantly evolving in structure, function, and scale. They generate an immense amount of data from various sources, including infrastructures, population, transportation, and environmental factors. Managing and analyzing this data is crucial for effective urban planning and development. The complexity of cities makes them both challenging and fascinating to study, especially when we aim to create digital models to simulate their behavior in real time. City information modeling and digital twin are revolutionary tools that allow us to monitor, control, and manage urban environments in real time. By using these data-driven approaches, we can simulate the city's infrastructure, predict outcomes, and make more informed decisions. This enhances urban planning, improves efficiency, and ultimately leads to smarter cities that can adapt to changes quickly and effectively. One of the most significant challenges faced by urban planner and designer, especially in developing countries, is the lack of integrated databases connected to urban models. Without these databases, it becomes difficult to create accurate and functional 3D model of cities. This gap limits the ability to perform comprehensive urban analysis and hinder the implementation of advanced tools like CIM and digital twin. Our study aims to address this issue by finding practical solutions for data-scarce environments. This diagram illustrates the relationship between city information modeling (CIM), building information modeling (BIM), and geographic information systems (GIS) in the context of smart cities. CIM integrates data from BIM and GIS to create a comprehensive digital representation of urban environments. This interconnected system allows for better urban planning and decision-making. The pyramid showcases how these technologies come together to support smart city development through evidence-based, data-driven processes. In this project, we focused on creating a smart 3D model of the Narmak neighborhood in Tehran. This model is designed to assist in urban planning, design, and management. By incorporating a wide range of data, this model can provide insights into the neighborhood and support decision-making processes, allowing for more effective urban development strategies tailored to local needs. Our case study focus on the Narmak neighborhood in Tehran, Iran, which consists of 14,602 individual lots. This area was selected due to its unique urban layouts, which presents both challenges and opportunities for smart city modeling. By analyzing these lots and integrating various types of data, we can better understand the dynamics of the neighborhood and create a 3D model that aids in urban planning, design, and management. This slide presents the methodology used to develop the 3D model for the Narmak neighborhood. Due to the lack of an integrated database, the data for this project was gathered from multiple sources. Building parcel data was prepared in ArcMap in shapefile format and then imported into CityEngine. Vegetation data was extracted from aerial imagery, while street data came from OpenStreetMap OSM. Additionally, some data like building facade images didn't exist at all and had to be collected manually through field photography. Data from various sources, including building lots, street networks, and vegetation locations, were collected and processed. These datasets were imported into CityEngine, where they were combined to create a comprehensive 3D model. The flowchart on the right illustrates the steps involved in data collection, preparation, and integration into the CIM and digital twin model. These models provide valuable insights for urban planning, design, and management. In this project, we developed a comprehensive urban database for the Narmak neighborhood. The database contains various attributes, such as land use, street width, building height, vegetation, and facade types. This data is integrated into the 3D model, allowing for detailed analysis and visualization of the neighborhood. By linking these attributes to the spatial data, we can gain a deeper understanding of urban dynamics and improve decision-making. In this step, we used Python scripts to automate the assignment of facade images to each building lot. By using attributes such as facade type and lot size, the script dynamically selects and assigns the correct facade code. This process allows for a more detailed and realistic representation of the urban environment. In this project, we use the level of detail LOD concept in CGA programming to manage the complexity of the 3D model. LOD allows us to adjust the amount of detail shown for each object based on its importance or distance from the viewer. By implementing various LOD levels, we can optimize performance while maintaining visual accuracy. This helps in efficiently managing urban modeling in CityEngine, ensuring the detailed information is only displayed when necessary. In this section, we focused on improving the accuracy of the first edge detection for building lots. CityEngine provides an option to calculate the first edge based on proximity to streets. But since road network data in Iran is often not precise, we enhance the accuracy by assigning a custom attribute to each lot. Using Python scripts, we then calculated and applied the first edge based on these attributes, ensuring a more accurate 3D model. In this section, we defined four main orientations: north, south, east, and west for each building to support 3D modeling using CGA programming. The orientation of each building is stored as an attribute, which is then read by the CGA rules. By utilizing the conditional rule in CGA, the correct orientation, north, south, east, or west, is applied to each building, ensuring precise and accurate 3D modeling based on its specific direction. In this section, we categorized the facades of buildings in the Narmak neighborhood into 10 distinct groups. Each group contains a database of facade images. When the Python script for type enamel is executed, it selects and applies one of the facade images to the corresponding building lot based on the assigned facade type. This method allows for a systematic and automated approach to applying accurate facade patterns to the 3D model. Now we have covered the methodology and techniques used in this project. Let's move on to discuss the results. In this slide, we compare real photographs of the Narmak neighborhood with the simulated 3D models generated in CityEngine. The images highlight the accuracy and details of the simulated environment. This simulation allows for a realistic representation of the area. As you can see, the facades simulated in the lower section of the slide, which were modeled in CityEngine, closely resemble the real-life facades of the neighborhood. In this view, we see a comprehensive simulation of all building lots within the Narmak neighborhood. The model accurately reflects the structure and layout of the entire area, with detailed 3D representations of the buildings. This slide illustrates the use of LOD in various aspects of urban modeling based on the context and purpose. Users can select the LOD for urban planning, where both 2D and 3D land use models are displayed. For urban design, facades are incorporated into the model. In urban management, city dashboards are added to the model, providing valuable insights that assist in decision-making processes. I'm going to show you a video that I recorded while working in CityEngine. This video demonstrates the process of interacting with the digital twin model of the Narmak neighborhood in Tehran. I'll now let the video run. I'll remain silent so you can fully focus on the video. In this slide, I'd like to highlight the CityEngine dashboard, which provides a wealth of data for urban analysis. The most important statistics include total land use area, floor area ratio, building facade types, building coverage area, number of buildings, number of trees, These key statistics offer valuable insight into the Narmak neighborhood and are essential for effective urban planning. The application of CIM and DTs in urban planning includes real-time data usage, simulating future land use, transport systems, and comparing land use chains. In urban design, it allows for visualizing city models, experiencing virtual spaces in 3D, and simulating urban facades. In urban management, CIM and DTs supports disaster management, urban infrastructure monitoring, and involve citizens with virtual models of the city, providing data-driven insights for decision-making through dashboards. In my future research, I'm interested in exploring the intersection of procedural modeling and AI. I find the combination and enhancement of procedural modeling, core of CityEngine with generative AI particularly fascinating. Thank you all for your attention. I hope the insights from this presentation help you understand the potential of digital twin, especially in data-scarce environments. If you have any questions or would like to discuss further, feel free to reach out via the contact information provided. Have a great day.